Here we are in section 2.4, and welcome to deductive reasoning. First concept that we need to discuss is the idea of deductive reasoning. If you remember inductive reasoning, right, back in the day, inductive reasoning, sometimes I use this upside down triangle. So you go through a whole lot of different examples to eventually come up with one solid rule, right? So that's inductive reasoning. Deductive reasoning is the opposite. It's like a triangle like this, where you've got a rule and then you use that rule to govern a whole bunch of examples. Huh? Kind of weird. Let me break it down. All right, let's get this out of the way. So what am I saying? I'm saying that deductive reasoning uses facts and rules to reach a logical conclusion, right? Not just looking at a bunch of examples and coming up with a conjecture, which is what we did with inductive reasoning, all right? So the next term that we're going to talk about is valid. Valid means logical or it makes sense. So when we talk about things being valid, we mean it's logically correct, meaning we can deduce it from the information given. It makes sense. It's valid. It's true. The next term we're going to talk about, the next two terms are kind of involved, so let's make sure they make sense to us. The first one is called the law of detachment, and the law of detachment is nicely summed up in this figure or key concept right here. So the law of detachment, in words, we've got a situation where if P implies Q is a true statement, so if we've got this true statement where P implies Q, then if P is true, we can totally say that Q is true. It's the law of detachment. So here's a nice example. If a car is out of gas, then it will not start. Sarah's car is out of gas. Guess what our valid conclusion is? That Sarah's car will not start. So you see that the law of detachment really just works with the hypothesis and the conclusion of a statement that's true. If we take the hypothesis implies the conclusion. If the hypothesis is true, then the conclusion is true. So that's our law of detachment. So once again, our law of detachment says that if P implies Q is true, then if P is true, we can assume that Q is true. All right? The next one is the law of syllogism. Sounds pretty fancy. The law of syllogism. And so we'll talk about that by looking at the key concept. Here it is. The law of syllogism has this quality of, watch it, it's almost like a chain of events. Check this out. If P implies Q and Q implies R are both true statements, then P has to imply R. Then P implies R is also a true statement. So let's look at it again before we get into the example. If P implies Q is true, and then Q implies R is also true, then we can kind of skip this middle step and say that P implies R. That's also a true statement. So let's take a look at our example. If you get a job, then you will earn money. If you earn money, then you will buy a car. So it makes sense to say that if you get a job, you will buy a car, right? If you get a job, then you will buy a car, because the P to Q, then Q to R, the fact that this is almost like a stepping stone, right? If I'm at P, I'm going to jump to Q, and if I get to Q, I'm definitely going to get to R. Then getting on P means you're going to R. Does that kind of make sense? I hope I'm not confusing you. All right, so that's our law of syllogism. One more time, just for kicks and giggles, our law of syllogism says if P implies Q and Q implies R are both true statements, right? Then what was the conclusion? Do you remember? Then P implies R is also true. All right. So hopefully that makes sense. And of course, anytime we have anything that's kind of weird like this, it's always going to feel better when we do some examples. So without further ado, let's get to a couple of examples. Here we are with example 1. We're going to determine whether each conclusion is based on inductive or deductive reasoning. Remember, deductive reasoning is where we're looking at a pattern and trying to come up with a rule or a conjecture, and deductive is where we start off with a rule or a law and we apply it to a situation, or we apply it to figure out a logical outcome. So let's look at part A. Every time Katie has worn her favorite socks to a softball game, she has gotten at least one hit. Katie is wearing her favorite socks to a game tonight, so she concludes that she will get at least one hit. So Katie's coming up with this belief, right? She concludes she will get at least one hit. What is this? What is she basing this on? She's basing this on observations, right? Previous observations from her life. Every time she wore her favorite socks, let me tell you, she got at least one hit. When we base things on observations or patterns in the past, that's inductive reasoning. So what Katie is using is inductive reasoning. Let's take a look at John's situation. If John is late making his car insurance payment, he will be assessed a late fee of $50. John's payment is late this month, so he concludes that he will be assessed a late fee of $50. So what do you think? It looks like to me that this would be, which one, inductive or deductive? There's a law that says you gonna get fined $50 for being late. And so he uses that law to assess his situation. He is indeed using deductive reasoning. Does that kind of make sense? I hope that helps out. So that's deductive reasoning. Let's take a look at a couple of other examples along these lines. So here, this next example is going to talk about the law of detachment. Again, the law of detachment just says if P implies Q is a true statement, then P being true means that Q is also true. And so we'll see if we can apply that in this next example. So here, law of detachment, we're going to determine whether each conclusion is valid based on the given information. If not, we're going to write invalid. So here, given two angles, if two angles form a linear pair, remember a linear pair is two angles that come together, and when you add them up, if you add up their angle measures, it's 180. They form a line when they're stuck together, right? So if two angles form a linear pair, then their non-common sides are opposite rays. They have one side in common. Their non-common sides, I'll highlight here, would be these guys. So the idea is that, do we think that we can come up with this conclusion? So the conclusion here is that given that situation, given the fact that AED and AEB are a linear pair, and they share obviously AE, that side, then the rays ED and EB, the side that they do not share, are opposite rays. That's the conclusion. So let's go back to our statement and see if this conclusion makes sense. I mean, it's feeling like it makes sense to me, but let's make sure it really does. So our given statement, our law in a sense, is that if two angles form a linear pair, that's my P, then their non-common sides are opposite rays. That's my Q, that last part. Their non-common sides are opposite rays. So that's true. That's a fact that we're going to hold on to. We are now told that angles AED and AEB form a linear pair. So that part is my P value again. That's P is coming up, right? So it's saying, hey, this is the true statement. Given that this is true, we can therefore lead ourselves to the idea that their non-common sides are opposite rays. Therefore, by the law of detachment, we can say that ED and EB are opposite rays. So that is a valid conclusion by the law of detachment. It's valid. Does that make sense? I hope so. I hope so. I know you'll let me know. Let's try this next one. Here, if Mika goes to the beach, she will wear sunscreen. All right. So here we have P implies Q. Remember, the law of detachment says if P implies Q and you've got that P is true, then Q is automatically going to be true. If P implies Q is true, so we're going to assume that that given information is true. If we then come up with a situation where P is true, then we can then assume that Q is true. Let's see if we have that here. If Mika goes to the beach, P, she will wear sunscreen, right? So what we have is Mika is wearing sunscreen. What do we have? We don't have P here. We actually have Q, right? We've got Q. We don't have P. So this is true. We have this. Is it necessarily true that Mika is at the beach? No, we can't say that. So this is an invalid conclusion. It does not follow the law of detachment, because the law of detachment says if P then Q, and then we get another P situation, or we get a situation that agrees with P, then we can imply Q. Here we got P and Q, but then we were given Q back again. I think I'm sounding crazy, but I know that this is making sense, at least a little bit. And if you're not feeling it, you're going to ask me about it. So I'm comfortable and confident in that. Talk to me. All right, let's look at this next one. We're going to talk about, we're going to kind of look at using a Venn diagram for analysis purposes. So here we are. We have to determine whether each conclusion is valid based on the given information. If it's not valid, then we're going to write invalid, and we're going to explain our reasoning using a Venn diagram. So here it is. If a primate is an ape, then it does not have a tail. Let's go back to that. If P, here's our P value. If a primate is an ape, conclusion, then it does not have a tail. All right? So let's think about a Venn diagram for our situation. So we might have a situation where we're kind of considering all primates, right? So this rectangle deals with all primates. All primates fit here. So if a primate is an ape, then it does not have a tail. In our conversation, in this statement, we see that we're dealing with primates, and we're dealing with some primates that are considered apes, and we're dealing with some primates that have tails. And we know that there's no overlap between these two groups, right? There's no overlap between apes and tail-having primates. So now the question is, where does Coco belong given our statement? Coco is a primate, so she belongs within the box, who does not have a tail. Well, we know she doesn't belong in this circle because this is the circle of primates that have a tail. So she could belong in this region with the apes, but she could also very well belong in this region that we haven't defined, that doesn't have, that's neither apes nor tail havers. So is the conclusion that Coco is an ape directly relatable to what we've said here? The answer is no. This is an invalid conclusion, because Coco could indeed belong to the apes, or she could just be a primate that doesn't have a tail but is not an ape. Because that was so awesomely fun and completely clear, let's go ahead and find out about the law of syllogism again, and let's talk about it. All right, so again, the law of syllogism says that if P implies Q and Q implies R, then we can say, and those are two true statements, then we can say that P implies R, and we looked at this example earlier. So here is an example that we'll look at. So determine whether the following statement follows logically from the given statements. So here we have, if you like musicals, then you enjoy theater productions. Let's call this P, and let's call this Q. Then it says, if you are an actor, that's neither P nor Q, let's call it R, then you enjoy theater productions. That's Q. So here we have P implies Q, and then R implies Q. Let's see if we can use the law of syllogism to confirm or validate any of these statements. If you are an actor, then you like musicals. No, we can't say that. We can't say R then P, because that would be R implies P. So this is not valid. We can't logically say that. Okay, let's try this one. If you like musicals, P, then you are an actor. Does P imply R? So P implies Q and R implies Q, but does P imply R? Let's look at the law of syllogism one more time. Do you remember before we said the law of syllogism goes from P to Q and then from Q to something else? Therefore, we can go from P to R. That's not what we have here. Let's look at this. We've got here in this next statement, if you like musicals, that's P, then you are an actor. That goes straight to R. It doesn't leapfrog from one to another. So this is also invalid.